So I was saying that at the crest, sorry, at the trough, and again at the trough only, induced EMF will be maximum. In between, EMF will not be maximum. I will explain that in another angle quickly to you. If you observe the car from a side angle, what I mean by side angle, if you see it from the side, now this is the road now, people. This is the road, okay? This is the road. So you have the trough, crest, and again the trough, like this. And your axle, now when you see from the side, it will look like this. 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 I hope you can understand. And let's take the axle here and here. Now here, the magnetic field, it is like this now, vertically upwards is where how the magnetic field is acting on the in that particular region, okay? And at the crests and trough, the axle's tangential velocity will be horizontal like this, so you can notice that the the direction of velocity and the direction of magnetic field, they are all perpendicular. So B, here also B, and B doesn't change. But in the midpoints, what is happening? Your car is moving this way. The axle's tangential velocity is in this direction now. Now, can I substitute B for the answer? No, I can't do that. I have to consider the component of that which is perpendicular to the direction of velocity, which is in this direction now. This is what I will have to consider. So if this is theta, this is going to become B cos theta. Same way here also I have to consider this this one. So B cos theta once again. So at this point, if you consider induced EMF, at this point induced EMF is directly going to be BLV. But at this point and this point, at these 2 points, in between points, induced EMF, what is the equation, guys? Tell me. Induced EMF will be what? B cos theta LV. B cos theta LV. Because you have to consider the component of magnetic field perpendicular to the direction of motion. So I'm saying at the crest and at the troughs, induced magnetic field will be maximum, but at the in between points, it will not be maximum. So at time is equal to 0, look, at time is equal to 0, they have clearly mentioned, at time is equal to 0, the axle PQ coincides with y axis. That's why I've drawn like this. Okay, so you can say at time is equal to 0, axle is at a trough. Okay, so I hope you guys got an idea. This is one of the challenging questions, but first you have to figure out, now here the direction of velocity didn't change, so your EMF can't go to negative side, because I have explained you VP will be higher than VQ always. VP will be higher than VQ all the time. If VP is higher than VQ, EMF at P with respect to Q, which is VP minus VQ, should be a positive value. So first answer, fourth answer, second answer can be ignored. Between 3 and 5, we have to consider the position of the axle and especially the tangential velocity of the axle, and decide where it's going to be maximum and where it's going to be minimum. Okay, people, I think we are done with that, and let me move on to the next question now. I think Ibrahim pointed out that we can do 45th one. Oh yes, brilliant. 45th one we can do. I don't know how I missed it. Thank you for pointing it out, Ibrahim. 45th one is from electric field, isn't it? Electric field. Charges in an isolated distribution of 3 plus q point charges are located at distances 2 centimeters, 3 centimeter, and 6 centimeter from point O. Another charge can be brought from infinity to point O without doing any work. Once a point charge of minus q is placed at a distance simple r from point O, the value of simple r is. Let's read it again. Charges in an isolated distribution of 3 plus q point charges are located at distances 2 centimeter, 3 centimeter, and 6 centimeter from point O. Let's draw that first of all. So we have a charge distribution. And This is my point 2. I'll take this as my point 2. And from point 2, we are placing 3 point charges. So all are plus q, plus q, plus q. And this gap is 2 centimeters. This gap is 3 centimeters. And this gap is 6 centimeters. Okay. So next, another charge can be brought from infinity to point q without doing any work once a point charge minus q is placed at distance r from point 2. So I have to place that minus q charge at a distance of point r from point O. I'll just say minus q at distance r. I am placing it on the other side because due to these plus charges on the right side, at O there will be a positive electric potential. There will be a positive electric potential. If you want to bring a charge from infinity to point O, and if you don't want to do any work at point O, the net electric potential must be 0. That's the idea behind this question. I will underline that part and write here. They're saying another charge can be brought from infinity to point O without doing any work. That means now at infinity, what is the electric potential, people? At infinity, electric potential is 0, and infinity electric potential is 0. Why? Because we know V is equal to Q over 4 pi r, 4 pi epsilon naught r, 4 pi epsilon naught r. When r is infinity, V has to be 0. That's the idea behind that, no, people? So for no work to be done, what is the condition? So for no work to be done, net electric potential at O must be what? Potential at O must be 0. Must be 0. Okay, well, again, if you want more explanation about that, because we know work done is equal to q bracket v1 minus v2. So if this is 0 q, and if this is also 0, then v2 has to be definitely 0, people. V2, so v2 has to be 0. Why did I put v1 0? Because that is at infinity, and if the work done is 0, q is not a non-zero value, so v2 also has to be 0, then only everything will be 0. So we have to make sure at point O potential is 0. At point O potential is 0. The net V net has to be 0. At point O V net is 0. That is where we are going to start. So if V net is 0 at point O, I'll write again. At point O, V net is equal to 0. What is the net electric potential, people? That is Q over 4 pi epsilon naught into 2 plus Q over 4 pi epsilon naught into 3 plus Q over 4 pi epsilon naught into 6 and minus Q over 4 pi epsilon naught into R equal to 0. Okay, so I think we can get rid of what, people? We can get rid of all the Q's. We can put 1 on top, and we can get rid of all the 4 pi epsilon naughts, correct? And if I simplify this quickly, I will be getting half plus 1 over 3 plus 1 over 6 equal to 1 over r. So our task is finding r. We'll take 6 as the LCM. Sorry, people, I had a connection drop. I'm so sorry. So I was explaining everything and I think I lost everything now. Okay, so this is where this is where I lost the connection, I think, when it stopped. Right, now what did we do after this? After we have figured out everything, it's all about just simplifying now. It's the maths work is remaining now. So you can cancel out all these q's, and 4 pi epsilon naught is common in everything. You can get rid of that as well, and you can take q to the other side and leave the numbers on this side. So it's half plus 1/3 plus 1 over 6 equal to 1 over r. and you can take 6 as common. It is 6 as common, and what is the number? I'm going to get here 3. What's the number I'm going to get here? 2. What's the number I'm going to get here? 1. 1 over r. So it is 6 over 6 equal to 1 over r, and 1 is equal to r. 1 is equal to 1 over r, sorry. So the final answer is r is equal to 1 centimeter. R is equal to 1 centimeter. That's it. So the answer is first one. Right. So Ibrahim, thank you for pointing it out, because it's a very good question. It needs a good deal of understanding. It requires a good deal of understanding regarding electric field for you to handle this question. So you need to know what they are talking about. So this term, so when the work done is 0, the electric potential difference has to be 0. Since we are bringing the first charge from infinity, already at infinity the potential is 0. So at O also the net potential must be 0. Then only net work done will be 0. Therefore, by the positive charges, there is a positive potential created here. There must be another negative charge which to create a negative potential here, so that it balances out and becomes 0. Right. So that's the end of this question. Let's move on to the next part. That is, so we are done with 45. I think we have to move on to 50th MCQ. Now, people, 50th MCQ. 50th MCQs is about electric field, obviously, because I can see plates and everything, charges and all. Let's see. A, B, C and D represent vertical cross sections of 4 identical parallel rectangular metal plates placed normal to the plane of the paper. Each of the plates A, B, C and D has a small hole at its center. The 3 plates are arranged so that their holes are coaxially placed as shown in the figure. Plate A is grounded. Okay, plate A is grounded means, people, the potential at plate A will be 0. No, plate A is at 0 potential. That is the meaning of grounded. And the entire system is in vacuum. All right. A stationary electron is created at time t equal to 0 at position O on the axis through the holes as shown. Which of the voltages which of the voltages VB, VC and VD should be applied to the plates to obtain velocity time curve shown in the figure B for the electron? So electron is moving starting from here. Electron is moving along this path. So as it moves along this path, its velocity is varying with time like this. So I will get rid of our B part. Now we know if this is a velocity time graph, we can draw an acceleration graph for this. Why am I going to trying to draw an acceleration graph, people? Because if I draw an acceleration graph, that will give me an idea about what graph. Acceleration graph and another time graph will be acceleration versus time graph, and another quantity versus time graph will have the same shape. What is that other quantity? For this, let's try to draw the acceleration time graph. Okay, this is acceleration. So acceleration time graph and something else. Can someone tell me what is that? Acceleration or resultant force? Resultant force or acceleration time graph. They both will have the same shape. Hope you can agree with me on this. Resultant force or acceleration time graph. So see, the object is initially accelerating at a higher rate, then it is decelerating at a lower rate, then it is decelerating at a extremely high rate, then again it is accelerating in the opposite direction, then again it is decelerating in the opposite direction. So let's try to plot these magnitudes in this graph. So first of all, it is accelerating, therefore the variation of velocity will be, acceleration will be like this, and then it is decelerating but at a lower rate compared to this. Here the gradient is high, people, so I have to draw even smaller. And then if you notice this part, it's a rapid drop. So there you can think of a very large deceleration like this, okay. And after that, what's happening? It is again accelerating in the opposite direction, but not as large as this one. These two look parallel to me. Let me see if they are parallel, people. Are they parallel? Yeah, no, somewhat parallel. Okay, they are almost parallel. So I think safe to say that they are parallel. Yeah. So this magnitude and this magnitude are going to be same. Where these two. And here the graph is accelerating once again. Are these two parallel? Do you think they are parallel? Okay, I've drawn a parallel line. Okay, see, and I'm taking it here, and let's see. Yes, they are perfectly parallel. So if you keep your rule and check, I think you will definitely be able to identify it. See, this one is parallel to this one, and this one is parallel to this one. So these two magnitudes should be same. Higher value, like relatively higher value. This is how the variation of acceleration should be. Acceleration, if that's the force, right? Okay, if that's the variation of force, people, we know force is equal to QE. Force is equal to Q delta V over D. So force F proportional to delta V. Why? Because so see, now force is directly proportional to potential difference, isn't it? Potential difference according to this equation. So wherever force is high, the potential difference should be higher there. Now I'll consider the potential difference here to be delta. Now for this interval, wait, we'll mark the time. Let's say this time is t1, let's say this time is t2, let's say this time is t3, let's say this time is t4, and let's say this time is t5. Now we have to understand something very clearly here. This is a very interesting question, to be honest. Now obviously people, electron is here when time is equal to 0. Okay, electron is here when time is equal to 0, and electron is definitely here when, wait, electron is, now electron is in fact doing this, people. It's moving like this, and it is coming to rest in the middle. See, where is it coming to rest? Now this region is A to B, this region is B to C, and this region is C to D. So electron, it moves somewhere here and it comes to rest, people, at this point, and then it is starting to move in the opposite direction. That's what the electron is doing. That's why the velocity, same parallel velocity graph, is on the other side. That is what's happening to the electron. It's like when you throw an object up, the object comes back down. Electron moves like this, stops and moves backwards. That's what's exactly happening. So if I mark the time, see if it makes sense. When time is equal to 0, electron is here. When time is equal to t1, electron is here. When time is equal to t1, electron is here. And when time is equal to t2, electron is here. When time is equal to t2, electron is here at this point. And when is this happening? This is happening when time is equal to time is between t2 and t3. This between t2 and t3, and that time is a special time. I don't know, or this one here, somewhere here. That we can take this time as t5, maybe t5. So that stopping is happening when time is equal to t5. I put t5, right? And it returns back. It moves in the opposite direction. So it's again there. It's again it is here when time is equal to t3, and it is again here, electron, when time is equal to t4, and electron is once again here when time is equal to t5. That is the meaning of this graph. So how can we know it hasn't reached D? Because if it had reached the Shimra, it would have gone with constant velocity in Shimra. There is no electric field after D. If it is not in the electric field, then it would have gone without changing its motion, right? Can't it reach D and come back? Yeah. I think look at the displacement is very small, no? Look at the displacement. Displacement is very small, right? this area is very small. So this triangle represents the distance between A and B. This trapezium represents the distance between B and C. So this small triangle is very small. So that's why. Okay. Even if it goes to D and comes back, it doesn't make any change in this question anyways. But I hope you get my point. And I hope everyone understood what's going on with this electron. Why this velocity time graph? The electron returns in the same path in the opposite direction. So here the electron is moving like this, and here the electron is moving like this, and it is returning to the initial position. So how is the area of triangle and trapezium? So I think it should be same. No, it should be same, because here between A and B have they mentioned that they are equal distance. The place are normal to the. They have not mentioned that they are equal distance or anywhere. Okay, I don't know whether this is drawn to scale, but according to the diagram, it doesn't seem like they are equal. But my point is, this area of this triangle should be the distance between AB. Area of the trapezium should be the distance between BC. Okay, right. So guys, now let's focus on the electron. Can you tell me the direction of forces acting on the electron? Let's mark that first of all. We'll forget about the rest. Let's mark the direction of forces acting on the electron at each area. That place, that in previous diagram is a little too messy, so I'm going for a new diagram, a bigger one. Tell me, what do you think are the direction of forces acting on the electron? Then you have D also. Here it didn't reach D. Electron is returning before it reached D. Because if it had reached D, it would have gone out with constant velocity. So here, what do you think is happening to the electron here in this region, in this particular region? Electron is definitely experiencing a force in which direction, people? Right, towards right or left? It is experiencing a force towards right. Why is that? Tell me. Because it is accelerating. Because it is accelerating. Electron is accelerating that way. So if this potential is 0, what should be this potential? What should be this potential? We know VA, okay, VA is 0, right? What is VB then? VB should be definitely what? Positive. VB should be definitely positive. VB should be definitely positive. Okay, so here electron in this region, electron is accelerating. Electron is accelerating. Force towards right. Okay, and what is happening to the electron in this region? Can someone tell me the direction? Can someone tell me the direction of force acting on the electron here, people? Hurry up. Here the force acting on the electron will be in which direction, people? It will be in the opposite direction, this way. I'll take it as F1. F1 because I'm going to compare that. Yeah, opposite. Why is that left? Because electron is decelerating. No? Here you can say electron decelerates. Not only there, here also electron is actually decelerating until this whole point. Electron decelerates first. I mean initially. Electron decelerates. So force towards left. It's slowing down. You can see in the VT graph. Therefore, electron is experiencing a force towards left side. Between F1 and F2, who is larger? Between F1 and F2, who is larger, people? F1 or F2? F1 and F2. Between F1 and F2, who is definitely larger? F2 is larger. F2 is larger because this deceleration's magnitude is very high. Okay, high deceleration. And tell me about VC then. Now VC should be repelling the electron. First of all, people, VB should be positive. No? First answer is wrong. VB should be positive. Therefore, first answer is wrong. First answer is wrong because VB should be positive. should be positive. Now in the second answers, we don't know what's the value of VB. It could be any positive value, but here, what can you say about this value? This value should be, now VC should be definitely, now VC here, this is VC. Tell me about what can you say between VB and VC, people? What can you say between VB and VC? Who should be larger? Between VB and VC, who should be larger? VB should be larger. VB should be larger. VB should be larger. That's why electron is decelerating. Now here VB was larger than VA, so this is like the positive plate, this is like the negative plate. Electron will accelerate towards it. Here electron is decelerating, means this is like the negative plate, this is like the positive plate. So this should be high potential, this should be low potential. So I have to choose an answer for VC which is lower than VB. Which answer is wrong? Fifth one is wrong. Fifth one is wrong because VC should be lower than VB. Between VC and VD, what can you say? Between VC and VD, what can you say, people? Hurry up. Between VC and VD, who is bigger? Between VC and VD? Hurry up, hurry up, hurry up. Between VC and VD, who is bigger? Again, VC should be larger, no? VC should be larger. VC should be larger. Why? Electron is decelerating. If electron is decelerating, this should be high potential, this should be low potential. Okay, this should be high potential, this should be low potential. So we have to choose answers where VC is larger than VD. This is wrong. Second one is wrong because in this one VC should be why is this is the answer wrong? This answer is wrong because VC should be greater than VD. That's why it's wrong. Between the third and fourth, people, VC is greater than VD. VC is greater than VD. Okay. So which one do you think is the most appropriate answer? Third or fourth? How do we decide the rest? Between VC and VCD, between VC and VD, there must be a huge difference. Between VC and VD, the difference must be huge. Between VC and VD, the difference must be huge because you can see from C to D, deceleration is extremely high. So VC minus VD, or rather, yeah, VC minus VD must be a large value. So when you consider that, people, which answer is the most suitable one? I think we can go with the fourth one. No, people? Can go with the fourth one. Right? This is why this is the 50th question. As it returns to it should have reached 0. As it returns, it should have reached 0. What do you mean by that? Should have reached 0. What should have reached 0? What should have reached 0, Shimra? I don't get it. What is 0? Velocity becomes 0. What do you mean? It should be 0. I don't get your point. Right. So what how I decided was between B and C, the potential difference is small, but between C and D, the potential difference should be very large. Look at this graph. Compare this and this. So in the third answer, that difference is not as large as the fourth answer. Yeah. So I think that's how I concluded it. That's how I concluded. This is just 0.1. Here it is 2.2 because this is 2.4 kilovolt. This is 0.2 kilovolt. But here it is 0.4 volt, the difference. Here the difference is 2.6 minus 2.8, 5.4. Large difference compared to that. So I think fourth is the best answer. So people, this question also is a lot to discuss. As the electron is moving in opposite direction in potential must have reached 0 between C and D. Between C and D, potential must have reached 0. Can we say that? No, right? No, it's not necessary. It doesn't have to be necessary, no? Doesn't have to be necessary. Now, if this is plus and if this is minus, or it could be plus and minus, both can be plus. It's all about the difference. So both can be plus, but this should be a high value and this should be a low value. That's all. So electron is returning not because this is plus and this is minus. Electron returning and this being plus and minus doesn't have any what do you call that? Any relation there, Shimra? Because whether this is high potential, as long as this is high potential and this is low potential, electron is going to continuously experience the deceleration. It will slow down, and when it comes to rest, it will return. No, we can't conclude that way. I think it's just about the potential difference. Okay, so for quickly, let's go through this again. We have to interpret this VT graph. We have to interpret the VT graph. We have to understand in what direction the forces are acting, and based on the direction of forces, we have to decide the potential difference, or just how the forces are going to act, and how the positive high potential and low potential must be arranged. Based on that only, we decide the potentials. So if it is accelerating from A to B, A should be low potential, B should be high potential, because electron gets attracted towards the high potential. So I will put it this way as a summary here for you to refer when you refer it later. If there is an electron experiencing a force towards right side, for example, there's an electron, and if it is experiencing an electrostatic force towards right side, meaning is this is high potential, this is low potential. This doesn't necessarily have to be plus or minus. High potential, low potential, you can always say this is plus and this is minus. Okay, it will be attracted towards high potential, and it will be repelled away from low potential. That's the idea behind this question. That's how you have to decide the potentials. Right. Okay, done. Try this again on your own and see if you can figure it out. This is a very good question, good practice. That's why this is 50th MCQ, people. When they put an MCQ as 50th one, usually we will have to do some extra work. Okay, but it's not very difficult. If you can understand how a VT graph works, then you should be able to understand how the electron is experiencing forces, and how the potentials must be. Okay, right.